there's so much more we can do. We can contribute in many different ways, big or small. For example, in driving the expertise when it comes to computational material science. A topic about which there's so much to say, I actually have to talk to 3 people about it. So please welcome from the University of Minho from Portugal, Professor Luis Sevino Alves Marques. We have 4 people actually from the Bergische Universität in Wuppertal. He just came in, he made it through the humdrum of all motor vehicles on the sound. It's Reinhard Henschke. Professor Reinhard Henschke, welcome.
Thank you very much.
Please join us. Then we have Frau Ulrich and Herrn Brambrink from Covestro. Also a big round of applause, ladies and gentlemen. So, I do not know how much you know about computational material science. Do you know a lot about it? No. You know nothing about it? Neither do I. So let's find out what it is. So I know you're a professor, and you're a professor too, and you know exactly what you're talking about, but we have an audience that would really like to understand first what we'll be talking about later. So, if at all possible, could you break down what computational material science is all about and why it is so important?
I think so. So the scope of computational material science is just to basically model and simulate the behavior of materials using computational techniques. In the end, what we want is to understand either or complement experiments to getting this information. In the end, if we are lucky, also to lead to the design of new materials with some kind of specific on-demand properties.
So basically, in the early days, you just put materials together in a little jar and you watch what happened. And now you don't have the jar anymore, you have a computer and you tell the computer what features the materials have, and then he himself computates what might happen or what will happen. Is that
with some help, someone with a brain behind.
You have a brain too? Yeah, you've got to use your brain in order to get the right stuff into the computer. Professor Henschke, is there anything you want to add in terms of us lay people understanding computational material science?
Well, yes, I pretty much agree with the other speaker here. In principle, I mean, to bring it to the point, I mean, you want to say if you want to design a new automobile tire and you want to reduce the braking distance or the rolling resistance, and then you should be able to tell, I mean, the compounders that you want to put in a different silane with a particular chemical functional group, and that will do the job, and you figure this out by computer. This is what it is, ideally, but it never works that way.
Oh, it never works that way. Okay, so why do you say it never works that way? Is it that there's so much the computer can't computate, or is it that the human being putting the knowledge into the computer has flaws? Why would you say that?
Well, the main problem is scale. If you think about molecules, you're on a scale of a nanometer. That's 10 to the minus. It's 10 to the minus 9 meters. Yeah, it's thousands of a millions of a meter.
Okay.
And an automobile tire, let's say, typically is on the order of a meter. Yeah. So if you want to connect these two very different scales, that is a huge thing to do. And time-wise, it's the same. If you think about how fast molecules move, you're on the picosecond scales. That's 10 to the minus 12 seconds.
Okay.
Yeah?
Right.
And so you need a million times a million more time in order to get to a scale where the tire is rotating on the road. So that's the big challenge.
Okay. So does that mean that the computer is actually slower than the lab? Because he has to go through all the computation and scale it, is that it?
That's basically it.
Okay.
We cannot do everything in computer.
Okay.
And so the computational material science, the development work, it's slower a little bit than in experiments. We can sometimes get answers faster.
Right. Okay. So that brings me to this side, to the Covestro side. I mean, you look at it with business eyes, so to speak. You're the industry that wants to use this as a means of digitalizing your company. Now, when you listen to this, what are the benefits from Covestro's point of view of honing in on this kind of process? Ms. Ulrich.
Yeah, We always look at it from two sides, and that is one perspective, what you kind of covered, the customer side. So how do we improve products for customers, and how can we really improve the properties of the product at the end, for the final use. But there is also the other application that we see, and that is kind of production oriented into our production, where we want to improve or increase the efficiency of processes, and also come up with new ways how to produce materials, which are energy saving, less material intensive, and so on. So these are the two directions where we see that material simulation can bring an advantage for us.
Right. So does that mean, Mr. Bramwijk, that we will lose the labs and only work on computers? I mean, they would say no, because sometimes the lab does really help. Do you see it the same way? Yes. Does it have to be both or either or?
Of course, it will always be both. So computational material science will not substitute the testing labs.
Right.
So, but I think they are complemented. So we get additional value from computational material science. So there's so much we can learn about that. So much in general, material behavior, really understand the principle of the materials, and we can use that knowledge, that know-how to transfer it into other simulations. So it will be both. But I think to have a vision for the future, it will go more into material science with increasing computational power. So what we are doing on molecular or atomistic length scale has been done since already several years. But with increasing computational power, we have the opportunity to do even more. So it becomes more important, but it will not substitute material testing, physical testing, yes.
Okay, I understand. So, Professor Henschel, we have lots of exhibits here that show where the industry is at the moment and where it can go, and it's all down to the material. And you already given us this neat example of the tire. Is there another example that you can think of to really break down the process of how you approach finding out about the features and the possibilities of a material?
Well, I mean, there's just a general approach. I mean, from the perspective of somebody like me working at a university, you have to learn how the product is made, first of all.
Okay.
Yeah? You know, in principle, just briefly coming back to the tire, to the rubber, I should be able to go to the lab, and given the equipment and given, I mean, say, the choice of raw materials, I should be able to put together a piece of rubber myself.
Mm-hmm.
Yeah? Then I understand, and this is true for almost everything that's here.
Yeah.
Whether you want to make a tire or want to make a lens system, you need a glue, for instance, to put in the lenses into a metal tube, or you want to make to attach strain gauges to a precision balance, something like this. Mm-hmm. You need to know what the product is all about, where its difficulties are, how that interfaces with the material, and then you can make clever choices by using the computer just in the right spot, so that you can actually, I mean, overcome the difficulty that I just pointed out about the scales.
Right. That's just, I mean, I see you not in agreement. That is what you meant. You still need your own brain. The computer doesn't do everything.
Basically, the computational material science will give you a further insight into what's happening in your materials. Mm-hmm. And so it will help you to develop them faster than what you would just do it if you just go to the lab and try by trial and error approaches.
Right.
So it's a clever way to develop your products faster.
Okay, it's a clever way. That's a very good idea. Now, talking about clever, I mean, what are the challenges when you work with polymers? I mean, you just had this rubber example, but lots of it is based on polymers. So, what's the specific challenge when you work with this?
Well, so polymers basically, so the problem is it's a scale. So it's large molecules, so you have to deal with this large scale problem, and that's basically when you go to computational techniques, when you deal with large problems, it's always difficult.
Okay.
So because you have a lot of things happening that you have to deal with, and a lot of interactions between molecules, and so it's a problem of scale.
It's a
and
problem
then
of scale.
when you mix different molecules and polymers, and then the problem gets worse. So
it gets worse. Okay. Let's see what you'd like to add.
Well, I mean, that's pretty much sums it up. I mean, it's more or less, I mean, time. Yeah? If you can take a raw piece of rubber which is not cross-linked, put it on a shelf, and then you can come back next day and it flows. I mean, you can buy the stuff silly putty for your children in a store. It flows. Yeah? Within, say, 20 minutes, it's after you have rolled it up to a ball, it's flattened out like a pancake. Yeah? If you do the same thing with a drop of water, it has been evaporated a long time before. Yeah? So water is a small molecule. It's much more, it's faster. The relaxation times that it needs to turn around is much faster. And so, and to make things worse, the polymer really connects all these scales. There are some fast degrees of freedom, as we call it, and then there are very, very slow things happening. And so you have to connect the two because they are intimately related and determine the property of the material.
Right. So if you compare this to pharmaceuticals, working with polymers, is that really so much more complicated? Is it a different approach also from the business point of view?
Yeah, it makes it more complicated because what was already mentioned, we are talking about large molecules and also macroscopic properties at the very end. And that means it does not really help to simulate only a small, tiny piece out of it, but there are properties that only can be simulated when you look at the overall molecule and not only one polymer molecule, but lots of them and their interaction.
Right.
And there are so many options in that, so that just eats up a lot of computational power as well.
Yeah.
And that's why we always have to balance how much detail do we need in the calculation and how much can we actually simplify to get a bigger sample and to predict then out of that bigger sample the macroscopic properties at the very end as well.
Okay, so so far we have a very basic understanding of what it does when you do computational materials science. We understand the complexities, just kind of, you know, the lay people complexities in it. But now we'll have to look at what happens if it works. I mean, what are the successes that you can report on with this new approach? Maybe Mr. Bramwink.
Yeah, so we can see here a lot of exhibits and parts on this case show on our booth, and so as an engineer we are bringing applications on the road. So we are finding new applications, new technologies, and as already discussed, we have this length scale issue, and with computational chemistry we were finding some mechanism, but it will not help us finally to develop real parts, real application. And this is currently the main challenge, to use the simulation tools as we have it today, like finite elements methods, for example, to really calculate the big parts with a meter length scale, for example, but extend this information with findings from computational chemistry. So that means we can sharpen our material models, we can make it more precisely, and then at least have better results, and we are able to faster developed products finally. Okay. So, and when I'm saying products, I mean application, real final plastic parts.
Sure. I mean, you just mentioned it. There's lots of exhibits on the Covestro stand. Is there any specific one that the audience, if they are interested, could go and look at, and you can explain how you went from computational material science to what we see here on the booth? Is there anything specific in any of the areas?
So finally, computational material science is in every of our exhibits here.
Okay.
That's for sure. What I'm saying is that the macroscopic parts we have need other simulation tools.
Right.
Yeah. And so for that meaning, we also need to find material data, write material data, need to characterize material data. And so that's what we are currently doing. And so in every part is already computational material science included here.
It's everywhere, as they say in English. So let's see, they're still there and they're still awake. So maybe they have questions. I mean, so far we've started off with what is it, what can it help us do, and what are possibilities when you apply it. So is there anything you would like to ask the ladies and gentlemen on this stage with regards to the possibilities, the challenges, what's behind it? Maybe you want to apply for a job or anything. So anything you want to know, just raise your hand. We've got 2 microphones here. There's one gentleman over there in the corner, right underneath the camera.
Yeah, Mike Roberts, how are you? What is your data strategy in the lab in terms of integrating with devices or building out data sets? Do you have a defined data strategy in the lab?
So it's a good question because we've got 4 people looking at each other.
Yeah. Can you just, for the benefit of us, repeat the question? I didn't really catch it.
You didn't really understand. Could you just one more time and really close to your mouth so they can hear it?
If the models are enabled by data, what is your data strategy in your lab?
The models are enabled by data. What do you exactly mean, enabled by data?
I assume you're talking about machine learning models.
Okay.
Okay.
Yeah, go ahead. Just speak into the microphone.
Maybe I can comment on that. I think, yeah, what you're referring to is not directly only the simulation of properties, but more the using of statistics, analytics, machine learning models, and so on. And of course, we have there the advantage of years of research data that we already have. And the strategy, of course, is to on the one hand, actually use what we currently already have and bring it into a format where it's actually clean data to be used in these data models. And then on the other hand, of course, enable the data collection that we're currently doing to be directly in a format that is much easier to use than the old ones. So of course, there is the data strategy behind it to use as much as we have and to join as much information into, of course, a data lake at the very end. And we'll see how big that actually gets and how much tests and probes we can take to enable new machine learning models out of this. So that is a branch of what we're doing as well, yeah.
So basically it opens up a new lab. It's just not that it has the little tubes, but you still have to go trial and error and find out what works and what makes sense in terms of the data now, rather than just putting stuff together. Okay, so that's the strategy is still we have to find out. Yeah, exactly. It's just now digital rather than physical or chemical. Okay, anything else you would like to know, ladies and gentlemen? Not at the moment? But you're still up for more information? Shall I ask them more questions? Yeah? Okay, I'll have a couple more because it's our signal, so stop talking, Carl. When you look at the customer side, I mean, this is, I try to understand, we try to understand, the customers try to understand. What's their reaction when you say, well, we just do computational models and here is your raw material or here is your application? Do they follow you all the way or are they shying away because it's not there, it's not tangible?
Well, thank you, Carl. That's a really a very good question.
Finally.
In engineering, and we're facing it in our daily work and also at our customers. So we are very much stuck in tested data. Yeah? So our customer, they're all also requesting test data, physical test data. And so if you want to offer kind of artificial or virtual material data, which is not coming from the lab, then the acceptance level is kind of limited. So they are always asking for tested data. I think currently we are in a kind of change. Yeah? So all the digital initiatives in different companies, they will create a new mindset. And so in the future, I think also virtual material data coming from computational material science will find a better and a higher acceptance. And that is also what we are striving for, that we not want to substitute the tested data we offer to our customer. We want to complement, but we also want to have a higher awareness and a higher acceptance. And I think we can reach that when we show the improvements we can make. Yeah, because in physical tests, there are a lot of things you cannot test. But material models, sometimes they request very specific tests which you cannot do in physical tests. And so we can do it with material science in a virtual environment. And this has added value, really, and this will improve the quality. And for that, I think we can convince also our customer for this new kind of data. And I think in the future, there will be a higher acceptance.
It sounds. Ah, my microphone's back. Just maybe to round it off, 2 questions to the science side of computational material science. I was once told by a chemical engineer that when you find something, you don't go, yeah, eureka, I found it. But a scientific reaction to a new finding is, that's odd. So is there anything where you did a computational material science test or worked with different materials where you went, oh, we didn't expect that. That's really a result that, how does that happen?
Well, that principle happens every day. Well, of course, you have to scrutinize what you see there and
sure.
and find out. I mean, on the science side, a lot of things do not work out right away.
Right.
Yeah? And a lot of things that you don't expect. And, well, sometimes you find something that you don't expect, and that later on turns out to be a big thing. And,
okay.
So that's nice, but that doesn't happen very often. But if it happens, it can make a big impact.
Okay. Now, talking about this, Professor Alves, when you interact with a company or the industry side, like Covestro, is there anything that you'd say, well, there's this one thing that I would change when I collaborate, which would make life or work so much easier for us? Is there anything like a top wish that you could voice now and everybody would listen to it?
Yeah, so working with industry in general, the problem is sometimes industry doesn't have the... They have problems, but then we have to ask the right questions.
Aha, okay.
Like this. Why doesn't this work? Sometimes it works better for us.
Right.
Because, well, so then it forces us to dig and look for what's going on. That's
right.
what, for example, it was in our case with collaboration with Covestro. It came from this part of, this is not working, we don't understand why. And
okay.
This was the motivation for research.
Right. So it's about asking the better question to you so you can deliver the more...
Asking questions and then talk with scientists and see what they have to say about it.
So is that something that really changes when you communicate with the science side? Do you have to think differently compared to the routine ways of going to the lab and trying out things? Or is it for you, it's the same kind of question mindset? You just say, I have this question, do it. It doesn't matter whether you use a computer or an organic lab.
So my answer would be it's probably pretty much the same because honestly we have scientists coming out of university who are trained exactly in that way of thinking and working, and we do not switch them as soon as they work for a company. Right. So the general approach is usually the same.
Right.
There might be some different questions when it comes to, how can we actually use it at the very end, but the approach is definitely the same.
Okay. Final question to you, Mr. Warmink. When you look at the successes so far, what was the thing that was most striking for you when you thought, I never thought that we'd get this application or down this road with a product or a polymer? Was there anything where you went, yeah? I'll give you a minute to think about it, and I'll ask them if they have any more questions. So is there anything else you would like to know from the science side or the business side when you deal with computational materials science, when you really have a computer rather than the lab giving you the results to work with? Is there anything else the audience would like to know? Yes, we have one more question here. I buy you some more time for your success.
What I would like to ask whether...
Microphone really close to the mouth.
So what I would like to ask whether you are modeling the polymerization, for example, in case of polycarbonates, the polymerization or the compounding of the materials.
That's you can share it between the four.
Well, it's both really. Yeah.
So both the structure of the molecule and the additives can be.
Yeah, you put in. Well, this is what I was talking about previously. I mean, there's a certain amount of knowledge that you need to put into this. I mean, if you have some material, it's usually composed of maybe 20 or 40 different things in the recipe, and you of course have to make a choice, and you pick the components which you think are most important, and then you look what happens. Because, I mean, every added component adds complexity and may also obscure the result to some extent. That's the nice thing about computers. I mean, you can really I mean, limit yourself to a number of components that otherwise wouldn't work in the real world, and see what they do if they come together.
Okay. Is this question answered? I reckon you're from the same field of expertise. You know what you're talking about. Yeah, yeah, kind of. Okay, so back to me not knowing what I'm talking about, but at least asking this one question. Is there anything that you remember where you go, that was really a brilliant moment working together with teams and using computational material science?
So I think very important applications are really the transparent applications with light integration, functional integration, and so there are so many more demands on the product than just mechanical properties. So electric properties, light properties, transmission properties, and so there's extreme collaboration inside Covestro. So for finally, bringing this part onto the road. Yes.
Okay, so it's a lot of the things that we can see when we look at the automotive showcase over there, where you have these translucent materials that you can only get when you do the computational material science beforehand. Excellent. So I suggest we'll go back there. It's on the other side of the booth, and you see there's this big concept car, and that is actually computational material science in the real world. This is what it leads to, what these gentlemen and what these two from Covestro do when they work together. For now, I say thank you very much to you for sharing it, for letting us into the world of science and the world of business, and to you for your attention, and this is your applause. Thank you very much. Have a brilliant time at the K Fair with Covestro.